Welcome to Grade 9, Unit 5 Cyberclass, Geometry and Measurement. This is Module 5.2, Further Work on Congruence and Similarity. This educational material was produced by eFanos, and your teacher for this course is Jane Goodland. The objectives for this module are to define congruence and similarity, to apply postulates and theorems in order to prove congruence and similarity of triangles, to construct similar figures, and to compare perimeter and area of similar polygons. Two plane figures are congruent if they have the same size and shape. Two plane figures are congruent if one figure can be moved so that it fits exactly on top of the other figure. So the small crescent and the large crescent are not congruent. Two triangles are congruent if their corresponding sides and corresponding angles are congruent. For triangles PQR and ABC, the length PQ is equal to the length AB, the length PR is equal to the length AC, QR is equal to BC, the angle at P is equal to the angle at A, the angle at R is equal to the angle at C, and the angle at Q is equal to the angle at B. So we say that triangle PQR is congruent to triangle ABC, and this symbol here means is congruent to. Two triangles are congruent if the three sides of one triangle are respectively equal to the three sides of the other triangle. So for triangle PQR and ABC, if PQ is congruent to BC, and PR is congruent to AB, and QR is congruent to AC, then we say that triangle PQR is congruent to triangle BCA. This is the SSS rule. So if all three sides of one triangle are congruent to all three sides of the other triangle, then the two triangles are congruent. Two triangles are congruent if two sides and the included angle of one triangle are respectively equal to two sides and the included angle of the other triangle. So for triangles PQR and ABC, if PQ is congruent to BC, and angle P is congruent to angle B, and PR is congruent to BA, then triangle QPR is congruent to triangle CBA. This is the SAS, or side angle side rule. If the side, the angle and the side of one triangle are congruent to the side, angle, side of the other triangle, then the two triangles are congruent. Two triangles are congruent if two angles and the included side of one triangle are respectively equal to two angles and the included side of the other triangle. So for triangles PQR and ABC, if angle R equals angle C, QR is congruent to BC, and angle Q is equal to angle B, then triangle RQP is congruent to triangle CBA. This is the ASA, or angle side angle rule. If the angle side angle of one triangle is congruent to the angle side angle of the other triangle, then the two triangles are congruent. It doesn't actually matter which two angles we use for this rule, because if we know two angles of the triangle, then we automatically know the third angle, so we could also use the angle-angle side, or AAS rule. Two right-angled triangles are congruent if the hypotenuse and one side of one right-angled triangle are respectively equal to the hypotenuse and one side of the other right-angled triangle. So for PQR and ABC, if angle Q equals angle B, because they're both right angles, QR is congruent to BC, and PR is congruent to AC, then we say that triangle QRP is congruent to triangle BCA. This is the RHS, right angle hypotenuse side rule, and it's also known as the HL rule, or hypotenuse leg rule. If two right-angled triangles have the same hypotenuse and the same side or leg, then they are congruent. Example, are these triangles congruent? XYZ with two angles on one side, and ABC with two angles on one side. We can use SSS, SAS, ASA, or RHS. First of all, we notice that there are angles on one and angles on the other, but not necessarily the same angles. So let's find the missing angle on the second triangle to make it easier to compare the two triangles. The angle at B is equal to 180 minus 110 plus 30, which is 40 degrees. We have two angles of 110 and 40 enclosing a side of 3 centimeters on this triangle, and two angles of 110 and 40 enclosing a side of 3 centimeters on this triangle. So yes, triangle ZYX is congruent to triangle ACB by the ASA theorem. Example: in the diagram, the opposite sides of the quadrilateral ABCD are equal. Prove that triangle ABD is congruent to triangle CDB. Prove that AB is parallel to DC and AD is parallel to BC. If we look at the two triangles, we've got this one here, ABD, and this one here, CDB. And we don't know anything about their angles, so let's have a look at their sides. We know that AB is congruent to DC, and also that AD is congruent to BC. We also know that BD, the diagonal, is a common side on both triangles. So triangle ABD is congruent to triangle CDB by the SSS theorem, the side-side-side theorem. Since we now know that the triangles are congruent, we know that angle ABD is congruent to angle CDB. Since we've got alternate angles here, we know that AB must be parallel to DC. Also, because the two triangles are congruent, we know that angle ADB is congruent to angle CBD. And again, alternate angles mean that AD must be parallel to BC. Example: show that O is the midpoint of both AQ and BP in the diagram below. We know that angle A is congruent to angle Q, because AB is parallel to PQ and they are alternate angles. We also know that angle B is congruent to angle P, again because of the parallel lines and the alternate angles. And we know that AB is equal to QP, because that's given to us in the diagram. So in these two triangles, we have two angles and an included side, which are the same in both triangles. So we know that triangle AOB is congruent to triangle QOP by ASA, or angle-side-angle theorem. This means that AO must be equal to QO and BO must be equal to PO. So O is the midpoint of both AQ and BP. Example: if ABCDEF is a regular hexagon, prove that triangle BDF is an equilateral triangle. Let's draw in the triangle BDF. We know that angle A, angle E, and angle C are all the same. And we know that all the sides of the hexagon are the same because it's regular. So we can use the side-angle-side theorem on these triangles here around the edge. Triangle FAB, that's this one here, must be congruent to triangle FED, which must be congruent to triangle DCB, by the SAS theorem, because they have a side, an angle, and a side which are equal in all of them. Therefore, FB must be equal to FD, which also must be equal to DB. That's the three sides of this triangle, and that means that the triangle BDF must be equilateral. Similarity. Similar figures have the same shape but not necessarily the same size. Here's a triangle ABC. Here's another triangle DEF. And here's another triangle XYZ. The three triangles all have the same shape because they all lie on the same rays coming out of this center point O. But we can see that they're all different sizes. Triangle ABC is similar to triangle DEF, which is similar to triangle XYZ. And this little line here means is similar to. We can say that one is an enlargement of the other. And we can say that angles in corresponding positions are congruent. and corresponding sides have the same ratio. Example: the two parallelograms below are similar. ABCD and PQRS. What is the size of A? If the shapes are similar, then they must have exactly the same shape, which means that their angles must be congruent. So this angle here at A must be the same as this angle here at P, so it's 110 degrees. Find the base SR of the large parallelogram. We know that the sides must be in the same ratio, so the ratio of BC to RQ is the same as the ratio of the base DC to the base SR. We can write that like this as a fraction. BC over QR equals DC over SR. So 3 over 7.5 equals 2 over SR. So SR equals 2 times 7.5 over 3, which is 5 centimeters. Example: is each statement true or false? Any two squares are similar. That's true, because all the angles are congruent, and the ratio of a side of the smaller square with the larger square is going to be the same whichever side we pick. Any two rectangles are similar. No, that's false, because you could have a long rectangle and a short rectangle. Any two rhombuses are similar. That's also false, because you could have rhombuses that have different angles. Any two circles are similar. That's true, because any circle is just an enlargement of another circle. Any two sectors of circles are similar. That's false, because you could have a sector with a large angle and a sector with a small angle. Any two equilateral triangles are similar. That's true, because the angles of an equilateral triangle are all 60 degrees, so a larger equilateral triangle will just be an enlargement of a smaller one. Any two isosceles triangles are similar. No, that's not true, because you could have a tall, thin isosceles triangle, or you could have a short, fat isosceles triangle. Any two regular polygons with the same number of sides are similar. That's true. If the three sides of one triangle are proportional to the corresponding three sides of another triangle, then the two triangles are similar. So if we have two triangles, ABC and XYZ, then we need the ratio AB over XY to equal the ratio BC over YZ and the ratio AC over XZ. And then we can say that triangle ABC is similar to triangle XYZ. This is the SSS, or side-side-side theorem. Example: are these two triangles similar? Let's test out the ratios. 2 over 1.4 equals 5 over 3.5 equals 4 over 2.8. We want to know if this is true or not. So let's simplify them to 20 over 14, 50 over 35, and 40 over 28 to remove all the decimals, and then cancel them down to get 10 over 7, 10 over 7, and 10 over 7. These ratios are all equal. So yes, the two triangles are similar by SSS. If the ratio of the lengths of two sides of one triangle is equal to the ratio of the lengths of two sides of another triangle, and the included angles are equal, then the two triangles are similar. So for ABC and XYZ, if the ratio AB over XY equals the ratio BC over YZ, and the angle between them, B, is equal to the angle Y, then we can say that triangle ABC is similar to triangle XYZ. This is the SAS, or side-angle-side theorem. Example: prove that triangle AOB is similar to triangle COD. Find the length of CD and prove that AB is parallel to CD. First of all, if we look at the two triangles, we see that they share a common angle in the centre, because these two angles are vertically opposite. So we can see that angle AOB is equal to angle COD, and we can now test if the ratios are the same for the two triangles. So if we test AO over OC, which is 3 over 7, and BO over OD, which is 6 over 14, then we can say that 6 over 14 is equal to 3 over 7. So they have the same ratios, so the two triangles are similar by SAS. Now we can find the length of CD by using the ratio. We know that AB over CD must be equal to 3 over 7, because it must have the same ratio as the other pairs of sides. So 5 over CD must equal 3 over 7. So CD is 35 over 7 centimetres. And now we can say that triangle AOB is similar to triangle COD, so angle A must equal angle C. But if angle A equals angle C, then we have two alternate angles, so AB must be parallel to DC. If two angles of one triangle are respectively equal to two angles of another triangle, then the two triangles are similar. So for triangle ABC and triangle XYZ, if angle B equals angle Y and angle A equals angle X, then we can say that triangle ABC is similar to triangle XYZ. This is because if you know what two angles of the triangle are, then you also know what the third angle of the triangle is, because the angles in a triangle always add up to 180 degrees. This is the AA, or angle-angle theorem. And notice that we don't need to know anything about the lengths of the sides. Example: prove that triangle ABC is similar to triangle CPD and find the length of AC. Triangle ABC here has two angles alpha and beta, and triangle CBP here also has two angles alpha and beta, so therefore the two triangles are similar by the AA theorem. Now we can use the ratios to find out the missing lengths. AC over CB is the angle opposite beta over the angle opposite alpha, so that must be equal to the angle opposite beta on this triangle, which is BC, divided by the angle opposite alpha on this triangle, BP. You need to make sure that you get the sides the right way around when you compare them. So AC over 15 must equal 15 over 60. So AC must be 225 over 60. AC is 3.75. If the ratio of the hypotenuse on one side of a right-angled triangle is equal to the ratio of the hypotenuse on one side of another right-angled triangle, then the two triangles are similar. So in these diagrams, if AB over DF is equal to BC over FE, then the triangle ABC is similar to the triangle DFE. This is the RHS, or right angle hypotenuse side theorem. Example: prove that the two triangles in the diagram are similar. Prove that AB is parallel to PQ. For the two triangles in the diagram, we know that this angle here must also be a right angle, because it's vertically opposite this right angle. So we have two right-angled triangles. We can now have a look at the ratios of the sides. This side here matches up with this side here, and this side here opposite the right angle matches up with this side here opposite the right angle. So BM over MP needs to match up with AB over PQ. So 8 over 12 needs to be equal to 10 over 15. But these two fractions are both equal to 2/3, so they are equal to each other. So we can say that triangle MBA is similar to triangle MPQ by RHS. So angle B equals angle P, or in other words, theta equals beta, and angle A equals angle Q, in other words, alpha equals delta. And so, by alternate angles, AB must be parallel to PQ. Example: prove that the segment joining the midpoints of two sides of a triangle is parallel to the third side and half of its length. On the diagram, let's mark the midpoint of AD and the midpoint of AE, and let's join them up. So we want to prove that the line BC is parallel to the line DE and half as long. If we look at the triangle ABC and the triangle ADE, we can see that both triangles share this common angle here. Also, the ratio AB over AD is equal to x over 2x, which is a half, and the ratio AC over AE is y over 2y, which is also a half, so they have the same ratio. So triangle ABC is similar to triangle ADE by SAS, side angle side. This means that angle BCE is congruent to angle ADE, and so BC must be parallel to DE. The ratio BC over DE must be equal to the ratio AC over AE, which is a half. So the short line joining the midpoints of the sides is half as long as the length DE. Ratio of perimeter and area. If we have two similar triangles and we label the sides of this one ABC, then we can say that the sides of the larger triangle are KA, KB and KC for some constant value K. The perimeter of the small triangle is A plus B plus C, and the perimeter of the larger triangle is KA plus KB plus KC, which simplifies to K times A plus B plus C. So the perimeter of the bigger triangle over the perimeter of the smaller triangle is K times A plus B plus C over A plus B plus C, which is equal to K. The area of the small triangle is half AB, and the area of the large triangle is half times KA times KB, which is half K squared AB. So the area of the bigger triangle over the area of the smaller triangle is half K squared AB over half AB, which is K squared. So the ratios of the perimeters is K, and the ratios of the areas is K squared. We can do the same thing with a rectangle. If the sides of the smaller rectangle are A and B, then the sides of the larger rectangle are KA and KB for some constant K. The perimeter of the small rectangle is 2 times A plus B, and for the large rectangle is 2 times KA plus KB, which is 2K times A plus B. The perimeter of the bigger rectangle over the perimeter of the smaller rectangle is 2K A plus B over 2A plus B, which is K. The area of the small rectangle is AB, and the area of the larger rectangle is KA times KB, which is K squared AB. So the area of the bigger rectangle over the area of the smaller rectangle is K squared AB over AB, which is K squared. So the ratios of the perimeters is K, and the ratios of the areas is K squared. If the ratio of the lengths of any corresponding sides of two similar polygons is K, the ratio of their perimeters is K, and the ratio of their areas is K squared. So P1 over P2 is equal to S1 over S2, and A1 over A2 is equal to S1 over S2 squared, where S represents a side, P represents a perimeter, and A represents an area. Example: two triangles are similar. A side of one is 2 units long. The corresponding side of the other is 5 units long. Find the ratio of their perimeter and their area. Well, P1 over P2 equals S1 over S2. So P1 over P2 is 2/5. The ratio of their perimeters is 2/5. And A1 over A2 is S1 over S2 squared. So A1 over A2 is 2/5 squared. So the ratio of their areas is 4 over 25. Example: the perimeter of two similar triangles is in the ratio of 3 to 4. The sum of their areas is 75 centimeters squared. Find the area of each triangle. We know that P1 over P2 is equal to S1 over S2, and A1 over A2 is S1 over S2 squared. So we can write A1 over A2 equals P1 over P2 squared. If we replace A2 with 75 minus A1, because we know that the sum of the areas is 75, then we can write that A1 over 75 minus A1 equals 3 over 4 squared. So A1 over 75 minus A1 is 9 over 16. So 16A1 equals 675 minus 9A1. So 25A1 equals 675. So A1 is 27 centimeters squared. Then A2 is 75 minus 27, which is 48 centimeters squared. Example. The diagram shows two similar figures. The areas of the figures are 5 and 7.2. The lengths of the bases are L and 6.9. Calculate the value of L. The ratio of the areas is equal to the ratio of the sides squared. So 5 over 7.2 equals L over 6.9 squared. So 50 over 72 equals L over 6.9 squared. The square root of 50 over 72 equals L over 6.9. So 5 over 6 equals L over 6.9, and L equals 5 times 6.9 over 6, which is 5.75 centimeters. Enlarge the triangle by scale factor 2, centre O. Draw the rays coming out from O. We need to enlarge the triangle, which means that we need to enlarge the length of the ray. So it needs to be twice as long. Do the same for the other corners. This gives us the coordinates of the new corners, and we can fill them in to create the new triangle. And we can check that the side lengths have been enlarged by a scale factor of 2. The side length here is 3, and here it's 6. So yes, this works. Enlarge the shape by scale factor 1/2 with centre of enlargement O. Draw the rays coming out from O. This time they need to be half as long, so the coordinate needs to go here. Do the same for the other corners, and mark the coordinate halfway along. Once you've done all the coordinates, you can join them up to create the new shape. Find the centre of enlargement and the scale factor for these two rectangles. For the centre of enlargement, we can join the vertices to create the rays. Where the rays meet is the centre, so the centre of the enlargement is here at O. For the scale factor, we can use the ratio A-D' over AD, which is 2 over 4, so the scale factor is 1/2. To summarise, the definitions of congruent plane figures are that they have the same size and shape, that one fits exactly on top of the other, and that their respective angles and sides are congruent. The definitions of similar figures are that they have the same shape, and that their corresponding angles are congruent. The ratios of the lengths of their corresponding sides are equal. Two triangles are congruent if SSS, the three sides of one triangle, are respectively equal to the three sides of the other triangle. SAS, two sides and the included angle of one are respectively equal to two sides and the included angle of the other. ASA, two angles and the included side of one are respectively equal to two angles and the included side of the other. RHS or HL, they are right-angled and the hypotenuse on one side of one are respectively equal to the hypotenuse on one side of the other. Two triangles are similar if SSS, the three sides of one triangle are proportional to the corresponding three sides of the other triangle. SAS, the ratio of the lengths of two sides of one is equal to the ratio of the lengths of two sides of the other, and the included angles are equal. AA, two angles of one are respectively equal to two angles of the other. RHL, they are right-angled, and the ratio of the hypotenuse and a leg of one is equal to the ratio of the hypotenuse and a leg of the other. If two similar shapes have sides in the ratio x to y, then their perimeters are in the ratio x to y, and their areas in the ratio x squared to y squared. If the scale factor of enlargement is greater than 1, then the image is larger than the object. If the scale factor of enlargement is less than 1, then the image is smaller than the object. Review questions part 1. Shape A is similar to B. Work out the value of x. Pause the video whilst you work it out. Here's the answer. X is 6 centimeters. The ratio of these two sides, 4.2 over 2.8, must be equal to the ratio of these two sides, x over 4. 2. Shape G is similar to shape H. The area of G is 210 centimeters squared. Calculate the area of H. Pause the video whilst you work it out. Here's the answer. It's 75.6 centimeters squared. The ratio of the areas is the ratio of the sides, 10 to 6, squared. 3. ABCD and DEFG are squares. Prove that triangle CDG and triangle ADE are congruent. Pause the video whilst you work it out. Here's the answer. Let's label this angle here x. Here's triangle CDG, and here's triangle ADE. AD equals CD, DG equals DE, and angle CDG is 90 plus x, and angle ADE is also 90 plus x, so they are congruent by SAS. 4. AB is parallel to CD. Angle ACB is equal to angle CBD, which is 90 degrees. Prove that triangle ABC is congruent to triangle DCB. Pause the video whilst you work it out. Here's the answer. If we label this angle x, then this angle is also x because they're alternate angles. The two triangles have this side in common, which means that they have angle x, this side, and then the right angle in common, so they're congruent by ASA. 5. The areas of two similar triangles are 45 and 80. The sum of their perimeters is 35. Find the perimeter of each triangle. Pause the video whilst you work it out. Here's the answer. The perimeters of the triangles are 15 centimeters and 20 centimeters. 6. Rectangle ABCD is mathematically similar to rectangle DAEF. AB is 10 and AD is 4. Work out the area of rectangle DAEF. Pause the video whilst you work it out. Here's the answer. Label the side AE x. Then 10 over 4 is equal to 4 over x, so x is 1.6. So the area is 6.4 centimeters squared. 7. Triangle PQR is an enlargement with centre O of triangle ABC. OAP and OBQ are straight lines. OA is 2, AP is 6, BQ is 7.2, and AC is 3.7. Work out the length of OB and PR. Pause the video whilst you work them out. Here are the answers. OB is 2.4 centimeters and PR is 14.8 centimeters. 8. SQ and PR bisect each other. Triangle RST is congruent to triangle WHAT by WHAT. Pause the video whilst you decide. Here's the answer. Triangle RST is congruent to triangle PQT by SAS or side angle side theorem. 9. The diagram shows two regular hexagons OABCDE and OFGHIJ. OAF and OEJ are straight lines. OF equals 3OA. The area of OABCDE is 4 centimeters squared. Calculate the area of the shaded region. Pause the video whilst you work it out. Here's the answer. The large area is 4 times 3 squared, which is 36. So the shaded area is 36 minus 4, which is 32. This is the end of Module 5.2.